You want to ask your question or?
Well, I just went through the only one. I just kind of make sure I did it kind of right. Was 35, 281.
So problem 35 and 281. Let's see. On 281. 13. 281. So you said 35. 35. Okay, so we have g of y. I'm going to write g of x. It's easier. Sorry about that. So it's x minus 1 divided by x squared minus x plus 1. And the problem is asking us to find the critical numbers. I just wanted to say this to you, that this expression is never 0. Furthermore, is always positive. Right? We discussed that last time? No? Yeah. It's coming from a cubed plus b cubed. Right? So this is very important because I will say that this function has domain all real numbers. It's very important to find the domain of the function, right? Because once I differentiate, the derivative may have a different domain. It doesn't have to have the same domain with the original function, right? Okay. Do I need to explain more on this? Okay. So now we differentiate and we get g prime. It's a ratio. The top prime is 1 times the denominator minus the top times the denominator prime divided by x squared minus x plus 1 squared. So obviously there's going to be no critical number coming from g prime being undefined, because when g prime is undefined, so is the function. However, they're both defined everywhere because this is never 0. So the only possibility will be that g prime is 0. So I'm going to try and simplify it as much as possible. X squared minus x plus 1. This is minus 2x squared and plus 2x. And plus x and minus 1. So I had 2x times x with minus in front. Then I had 2x times negative 1 with minus in front. Then I had negative 1 times x with minus in front, and negative 1, and another 1. Bless you. So these two go away. These two go away. Nice. And so now the numerator is negative x squared plus 2x. Divided by x squared minus x plus 1. And I factor out negative x, and I get x minus 2. And x squared minus x plus 1, everything squared. So all these are just algebra, absolutely necessary. So when I'm sorry, exactly. So 0, x equals 0, and x equals 2. These are the critical numbers. Now, in order to identify whether they turn into anything, then we have to study the sign of the first derivative. The sign of the first derivative. We have to study the sign of the first derivative. Okay, let's do it because of your question. Okay, this doesn't say anything. The only thing that I can say is that this is positive. I cannot say anything about this. Okay, so in order to study the sign of all this, I would have to study the sign of negative x times x minus 2. So I recommend this chart. And negative x times x minus 2. So we have 0 and 2, 0 and 2, 0 and 0 for the product. Negative leading coefficient, it looks like this, from positive to negative. And this one has a positive leading coefficient, it looks like this, from negative to positive. So it's negative, it's positive, and it's negative. So at 0, the function has a critical number, and the derivative changes sign from negative to positive, which means it will be a local minimum. At 2, the first derivative change is 0, so it's a critical number, and it changes sign from positive to negative. So this point, when x is 2, will be definitely a local max. But I have to study the sign of this expression. This one will not change anything. I will not even look at it. It's always positive. But this product could be positive or negative. It's positive when x is between 0 and 2, and it's negative outside, to the left of 0, union to the right of 2.
So I just want to refresh my memory.
Yes.
But, so the positive means it's above the x line.
So when I graph a linear function, yes, what is below the x-axis will be negative.
X-axis.
Yes, what is above will be positive.
Okay.
Yes. So that's why this one has a negative leading coefficient. It comes from positive values. It crosses the x-axis at 0, and then it becomes negative. Also, if you don't like this method of end behavior, then you can plug in a number. So between this and this, I'm going to plug in negative 10, so it's positive. Between the 0 and infinity, I'm going to plug in 2, so it's negative. Whichever works, whichever is better. Bless you in case you're sneezing.
Thank you.
Okay, is this clear? Is this clear? Okay, so let's take a look at and finish up number 49. So limit as x approaches 1 from x over x minus 1 minus 1 over natural log x. Okay, so in this case, we are asked to find the limit. So if you remember a month and a half ago, we started with limits, right? That's what we studied in chapter 2. In chapter 3, we looked at derivatives, which are also limits. A derivative is a limit of a difference quotient. And now in chapter 4, we look at limits again because they are so important when we graph a function. And this is in for applications of L'Hopital's rule. Okay? So we can't get away from limits. In chapter 5, we will get away a little bit from limits. However, they will come back in Calc 2 because not all integrals can be determined without limits. So please do not forget limits and appreciate them, please. Okay, so I cannot separate this into limit of this minus limit of this because the limit of this is undefined. It doesn't exist, I should say. The function is undefined at 1. So the only chance we have in this situation is to find the least common denominator, which is x minus 1 times natural log x. Multiply the top of the first fraction by natural log x and the top of the second fraction by x minus 1. So then we have x, natural log x, minus x, and plus 1. So far, so good? This is, I think, where we left it off last time. Perfect. So now, I'm going to have to try and see what it is. Because I knew that from the beginning, I couldn't use, no. I could not use limit laws. I could not separate the limit into a difference of two limits. That was not possible. So now I'm trying to see if it's 0 over 0 or infinity over infinity, because if it isn't, I cannot use L'Hopital's rule. So when x is 1, this is 0, and this is negative 1 plus 1, which is 0. So the top is definitely 0. This is 0, and this is 0. So the bottom is 0. So both conditions of L'Hopital's rule are fulfilled, meaning a ratio and 0 over 0. So we will differentiate the top as if it is by itself. So now remember, we will never ever do that to a function. We can only apply this procedure only if it's a limit and only if it's a ratio. And only if it's 0 over 0 or infinity over infinity. We never ever differentiate like that. Okay. So the numerator is a product. So the first function prime is 1 times natural log x plus x times natural log x prime, which is 1 over x, and then minus 1. And this prime is 0. Now I have to be careful because there is a product in the denominator as well. The first function prime is 1 times natural log x plus x minus 1 times 1 over x when I differentiate the second function. Are we okay so far? Yes, everyone? Okay, so obviously x over x will be 1, and 1 with -1, these two will disappear. Agreed? So this is limit as x approaches 1 from the top is natural log x and the denominator is natural log x. When I distribute x or 1 over x to x, I get +1 and -1 over x. Why I did that is because I prefer non-products in case I need to differentiate again. So x over x will be 1, and -1 times 1 over x is -1 over x. Now I have to try again. When I plug in 1, the top is 0. This is 0, 1. 1 minus 1 is 0. So this will be the second level. I still have a limit. I still have a ratio. I still have 0 over 0. All conditions of L'Hopital's rule are fulfilled, so I continue.
So you could do it unlimited times.
Unlimited, as long as it's a function, it's a ratio, and it's 0 over 0, or infinity over infinity. I can continue forever. So this is limit as x approaches 1. The top is 1 over x. The bottom is 1 over x. This prime is 0. Now I have to remember, that's why a long time ago I said, please commit to memory the derivative of 1 over x. How much is that? -1 over x squared. With minus in front is +1 over x squared. Okay, now I try again. Well, the top is 1, and the bottom is 2. So the limit is 1/2. Any questions on this? Okay. So this was problem 49. This was just a taste. So this was 49 on page 308. Okay, we're not that far yet. I just wanted to give you a taste of 4.4, but I still have several type of problems on page from 4.3. So back to 4.3. If you'd like to choose, I'll be more than happy. Please choose a problem from 24 through 29. 298.
What were the numbers?
I'm looking at sketch the graph of a function that satisfies all the given conditions. I'll tell you what I would like.
26.
I would like,
Whatever you like.
I would like 25 because it's in red. When something is in red, they normally say, oh, that's important. So that's one option. But I'll do any problem you want.
25 sounds great.
Okay, so let's take a look at 25. So it will take a while till I copy all this. So f prime of 0 equals f prime of 2 equals f prime of 4 equals 0. Then f prime of x greater than 0 if x is less than 0 or x is between 2 and 4. F prime of x is less than 0 if x is between 0 and 2 or x greater than 4. F double prime, the second derivative, is greater than 0 if x is between 1 and 3. And the second derivative is less than 0 if x is less than 1 or x is greater than 3. Why I consider this a good exercise is because, first of all, it will help us with the table, understand how important that table, or summarizing, maybe not the table, but summarizing the information we have, how important that is. So what do you think I'm going to do? I'm going to create a table. Thank you. And of course, f prime is first, f of x is in the middle, and then the second derivative. I see these numbers 0, 2, and 4. So f prime of 0, 2, and 4, they're all zeros. So I'm done with the first condition. then it says that the first derivative is positive to the left of 0 or between 2 and 4. I'm done with this. Then it says the first derivative is negative between 0 and 2 or to the right of 4. Done with that. The second derivative is positive. Now I have to insert a 1 and a 3 according to this. So I don't know anything here, what's happening. Okay, I have no idea. But I do know that the second derivative is positive for x between 1 and 3. Done with that. And it's negative to the left of 1 or to the right of 3. Done. Now, in the middle, I can put whatever I want. In here, 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 and here. I don't have any indication. I'm not restricted to any particular number in those 5 dots. It can be anything I want. Okay, so all the information is summarized. Obviously, here's what I know so far. That 0, this number is definitely a local, of course, because the signs are positive and negative. So this must be a local max. No question there. Now, what about 2, this number, whatever that may be? Yes, is a local min, because the function has a critical number. The first derivative is 0, and it changes sign from negative to positive. And, of course, this will be a local max. Okay, this is what I know so far. Also, I do know that when the second derivative is negative, then the function has to hold water, which makes sense. If you would like to use the second derivative test, this must be a maximum. Because it doesn't hold water, I meant to say. Sorry, it does not hold water. Okay, here it does hold water. So obviously this makes sense that 2, whatever must be a point of minimum. And here it does not, again, so obviously this must be a local max. Okay, so let's attempt the graph, keeping in mind what we have discovered and the summary of this chart. Again, these numbers don't count. Just making sure that this is a local max when the function is opening downward, local min, and I can consider these because I don't have any information about the second derivative. I can consider them inflection points because the second derivative changes sign, and this is another inflection point because the second derivative changes sign. I'm not told that the function is undefined there. I can create it as being undefined if I want to. I can say these are inflection points if I want to. If you don't want to, you don't have to. But as long as you keep the concavity as discussed. Okay, so on 0, 2, and 4. So 1, 2, 3, 4. So this is 2, 4, 1, and 3. So here's my graph. There is more than one correct answer, of course. So at 0, 0, it has, at 0, whatever, the function has a local max. So I will be graphing it. It doesn't matter how. But I have to make sure that at 1, it changes concavity. So I'm going to do this. That's my choice. You don't have to have the same choice with me. So at 1, obviously it changes concavity. As you notice, I didn't even care for the height of these points. So at 2, it has a local minimum. So here changes concavity, and I can do this if I want to. As long as at 3, it changes concavity again. And then it opens, yes, it opens downward. It has a local max at 4. And then I can do whatever I want. So this is an example of f of x. This is what I came up with, and you can come up with anything else. Any questions? Okay. Back to page 299. I'm looking at the graph of a population. Let's discuss that. It just caught my eye. 61. A graph of a population of yeast cells in a new lab culture as a function of time is shown. So this is time in hours, and this is number of yeast cells. Okay. Describe how the rate of population increase varies. So obviously, first of all, this function is always increasing. Would you agree?
Yes.
Which means its derivative is always positive. Awesome. So obviously, from here, we see, let me see if I can show this better with a pencil. Okay, so right here, the slope is this. But look what happens to the slope. Right? Right. So then here, something happens because all of a sudden it starts decreasing. Close to, yes. Still positive, right? But decreasing. So where is the slope maximum? Right. So about 8. I agree. So describe how the rate of population increase. Okay, so it starts, I wouldn't say close to 0, but maybe close to 1/2. It starts increasing till 8, and then it starts decreasing. I would say maybe towards 0, right? Okay. When is this rate highest? We already established that. On what intervals is the population function concave upward or downward? So, right. Concave up, concave down. Perfect. Estimate the coordinates of the inflection point. Yes, it says yes. So 8, I don't know, maybe it's 400 or 350. I accept both. So this is an example in which we, by simply looking at the first derivative, we can make sense of when and for which x value the rate is highest. Okay. Do you think we need more examples, or can we go back and practice some more with L'Hopital's rule? I do remember, and please correct me if I'm wrong, I do remember looking at situations with infinity minus infinity. I do remember 0 over 0. I do remember infinity over infinity. I think I do remember 1 to infinity. We had an example or two, and we should go back to another few. I think we had 0 to infinity. I don't remember if we had infinity raised to 0. Okay. Was there anything else?
Isn't there 7?
I'm sorry?
Isn't there 7?
Yes. So we had these. I remember these when we determined the limits with square roots, x minus the square root, and so on and so forth. And these are the powers, ratios, difference. And I'm missing one. What is the last one we are missing? 1 to infinity, 0. Yes, there must be 7. They're in the back of checklist 1 and also in checklist 2. Infinity minus infinity, infinity over infinity, 1 to infinity, 0.
0 times infinity.
Yes, that's what the product. Yes, I forgot the product. Thank you. That was 1. Just one product. Powers, ratios, one difference, and one product. Good. Thank you. Okay, so on page 308, you can choose anything you want from 15 through 66 in order to practice L'Hopital's rule on page 308. But I do have to choose something with powers, like you choose 63 or 65 or 59 or 61 or 55 or 57.
Maybe 57.
57 it is. So let's start with 57. Where are you, 57? Okay. Oh, because it's red?
Yeah.
Very good. Let's see. Why is it in red? X approaches 0. And 1 minus 2x. And everything raised to 1 over x. Perfect. So I will plug in 0, and let's see what we get. The base is 1, and the top is, yeah, oh, well, kind of 1 to infinity. But you're right. Okay, perfect. So this is one of the indeterminate cases. It's a power. Okay, what do you think we're going to do? Think for a moment. It's a function raised to a function, and this is what we always do. Yes, I have to denote it first. I have to say let y be 1 minus 2x raised to 1 over x. This is the first step. And the second step, yes, I will have to apply natural log to both sides. Oops. So natural log y equals 1 over x, natural log of 1 minus 2x. We agree so far? Okay. Now, I do have a new function, right? Natural log of y is not the original function I had. This was y, right? But now I'm looking at a different function. That is natural log y. I will determine the limit. So here's the concept. I will determine the limit as x approaches 0 from natural log y. And let's say I will get this. What will I have to do next? I just want you to have the layout of the steps. Let's say I calculate this and I get this. What am I allowed to do that? Not always, but these are all continuous functions. And I'm allowed to swap the operators. Yes, so from here, I'm going to take the natural log outside, and I'm going to write natural log of limit of y as x approaches 0 is this, and then I will be able to identify the limit that I'm really looking for. So that's the idea. So we denoted this function by y. We applied natural log to both sides. We will be determining the limit of the natural log, assuming we get whatever. And then we are allowed, based on continuity, only based on continuity, we are allowed to swap the two operators. And we will say the limit of this is this, and we will be able to find the limit of y. So now let's go back and do that, exactly what we just said. So we want to calculate the limit of natural log y as x approaches 0, which is limit as x approaches 0 from natural log 1 minus 2x divided by x. So far, so good? Is this the natural log y? Yes. That's what we just determined. Natural log y is 1 over x times natural log. Good. So now I have to try again to see what this means. So when I plug in 0 at the top, I get 0. When I plug in 0 at the bottom, I get 0, and I'm very happy with the result. I wasn't happy at all with this. Why? Why I'm not happy with this, but I'm happy with this?
L'Hopital's.
because I can use L'Hopital's rule, and here I cannot. Natural log helped to change 1 to infinity into 0 over 0. Good. So then I say limit Sx approaches 0. The derivative of the top is 1 over 1 minus 2x and multiplied by negative 2. And the denominator is 1. So now the numerator is negative 2, and the denominator is 1. So the whole limit is negative 2. So I'm going to copy the starting point, which is limit as x approaches 0 from natural log y, which is negative 2.
Hold on 1 second.
Swap the operator.
And now I will swap the operator.
So what happened to negative 1 or 1 minus negative 2x?
Plug in 0.
Is that okay,
Yes.
everyone? Okay, so now because all these functions are continuous, I'm allowed to swap. So this is natural log of the limit as x approaches 0 of our function y is negative 2. And now I have to think, because there is only one number whose natural log will equal negative 2. And that will be the result of the limit of y when x approaches 0. I only have to identify this. Once I identify this, I'm finished. I determined the limit of the original function. What could this be? 5? No. 25? No. It has to be a base of e and some exponent that will be brought in front. So it must be e to which power? That's it. There is no other number. We bring negative 2 in front, and natural log e is 1. So all this piece must be e to negative 2. Only natural log of e to negative 2 will give us negative 2. So coming back to our answer, to our problem, we were asked to find the limit as x approaches 0 from 1 minus 2x raised to 1 over x. And the answer is e to negative 2, or 1 over e squared. Yes, we need more practice on these problems. They're not trivial, but they all have the same background. And I think we should look, we did look at few, but I think right now is the time to look at these, because that's where they come into play in this chapter. Okay, I'm ready. Would you like to choose another, please? Is this clear, first of all? Any questions? Is there any question here? Is it clear how we got this number? Yes? Okay, so let's practice. Please choose another.
37.
Okay, 37 it is. 37. 37 is not this type, but that's okay. Let's and then we'll come back and
But what are the numbers?
the ones with a function raised to a function. But that's okay. Let's do this one first. We take a break from that, or we come back. It's fine. This is a good choice. Ax plus a minus 1 divided by x minus 1 squared. That's fine. So all these with a function raised to a function are from 55 through 66. That's okay. This was a good choice. Okay, so we're given another limit, and we're asked to find the limit. I have to plug in 1. So 1 raised to a, well, a is not infinity. This is, a is a constant. So this 1 raised to any constant will be 1. Then minus a, 1 minus a plus a minus 1, this is definitely 0. And 1 minus 1 squared is definitely 0. And we like this because it's a ratio. It's 0 over 0, so we can apply L'Hopital's rule. So then this is limit as x approaches 1. And let's see the top.
The AX to
Yes,
A
awesome.
minus 1
Very good. Minus a
over X to the
2 x minus 1 times the inner function prime, which is 1. At this point, I have to check again. Are you with me, everyone? Is this okay? Okay, now I have to check again when x is 1, a
minus that is
times 1 minus a is
0.
good. 1 minus 1 is good. So again, this is like I start again, right? This is a function, it's a limit, it's a ratio. It's 0 over 0. I can apply L'Hopital's rule. So this is limit as x approaches 1. So a times a minus 1 times a, I'm sorry, I meant to write x, to a minus 2 over 2. Because it's 2x minus 2, and when I differentiate 2x minus 2, I get 2. Here I had an a, I had to bring down a minus 1 and subtract 1 from the power, and this differentiated is 0. So when x approaches 1, this will approach 1. So this is a times a minus 1 divided by 2. Very good pick, actually. Any questions on this problem? Problem 37? Is this okay? Okay, so let's choose another one with a function raised to another function so we can do the swapping of the operators and
What were the numbers
yes,
to choose from?
yes, 55 through 66. Let me write it down. 55 through 66.
64.
Six-
Well, that might be on. I'm not sure if that's one of the. We
Well,
can do 63.
Or we can do 63. Very good. 63 is fine. 63, limit. I think it's x approaches 0 from the right.
Yep.
Okay, and 4x plus 1 raised to cosine. No, it's not
Cotangent.
cosine, it's cotangent. Okay. You want to work on this for 2 minutes on your own and see what happens? No. Okay. Then you're going to look at me and I'm going to look at you for 2 minutes. Yes, John? 2? Okay. So please work on this for just 2 minutes and we'll do it together, of course. Just give it a try.
Do we start our stare down?
Say it again. Yes.
What is that concept there? It's
So it's 63, limit 4x plus 1 raised to cotangent x as x approaches 0 from the right. Thank you. Sorry about that. It's a very important procedure and we need to know one problem like this will be on the test and the final. Yes. So first of all, we have to, we know this, yes we did, to apply natural log. So you have the natural log of y, not sure what this is. So let's write natural log y, yes, that's perfect. So now let's write limit of the natural log y. Like you did apply natural log to both sides, so we're gonna apply limit to both sides. So limit as x approaches 0 from the right, in parentheses, natural log y.
close the parentheses, equals, limit as x approaches 0 from the right, from cotangent x times natural log of 4x plus 1. Is that better?
So we are all in the clear. We denote this function by y, correct? 4x plus 1 raised to cotangent x. That's the first step, correct? Okay. Can anyone give the second step? So we are all on the same page? Right. So I have natural log y equals cotangent x times natural log 4x plus 1. I jumped, and I should have identified first the case. So when x approaches 0, this is 1. What about cotangent? Remember, cotangent is cosine x over sine x, which is 1 over 0. Again, it's the same thing. I would say that one of the ugliest, or most ugly. Okay, say it again. Yes. So after we denoted y, the function by y, and we apply natural log to both sides, now we apply limit to both sides. That's the next step. Very good. So I have limit as x approaches 0 from the right of natural log y equals limit as x approaches 0 from the right from cotangent x times natural log 4x plus 1. Now I try again. Obviously, it's infinity times 0, which is a much easier indeterminate case to handle than 1 to infinity. And I'll show you in a minute why. So 0 from the right, this is infinity, and this is natural log 1, which is 0. However, by a simple algebraic manipulation of this expression, we'll change it into 0 over 0. One advice: never try to move natural log anywhere. So if you have natural log in the problem like this, do not try to bring it down. It's going to be a total disaster. Do not touch natural log. So then I have to work on the other one. So is there any way I can change cotangent into something else that will create the whole thing, or make the whole thing to be a fraction? Yes, but I prefer 1 over tangent. Because I don't want a product. I don't want to have a product and also a denominator. So this cotangent x is the same with 1 over tangent x. That's what I want. So I want then limit as x approaches 0 from the right from natural log 4x plus 1 over tangent x. I'm hoping now that this is 0 over 0. Or infinity over infinity, if that's the case. But it's a ratio. It's no longer a product. It's no longer a power. So it's a ratio, and I'm hoping that this is 0 over 0 now. So, although I have to say cosine over sine is not bad, because the limit of cosine is 1. So it's not going to be any problem, but you have to separate it. You have to be careful, because if you keep them in there as a product at the top, it will take forever. So that's what I want to avoid. Okay, but if you change this into cosine over sine, then you separate limit of cosine times limit of natural log over sine. Because you are allowed to. One of them is 1, and the other one we work on. And it will not be undefined or indeterminate. Okay, so now the top is 0 and the bottom is 0. Because when x approaches 0, tangent approaches 0. Would you agree? Perfect. So now I'm in business. First of all, a ratio, and then 0 over 0. One more time, what happened here? A simple algebraic manipulation helped us to change infinity times 0 into 0 over 0. Okay, so please remember, do not touch this. Do not try to bring this down to say, oh, it's infinity over infinity if I put 1 over log. with power -1, because then you have to differentiate log raised to power -1 by bringing -1 in front and subtracting 1 from the power, and disaster. Okay, so the top, when we differentiate it, we get 1 over 4x plus 1 times 4. And the denominator is very elegant, secant squared x. And what is the answer? Where does this go? Yes, because this is 0. Where does this go? Exactly. So the limit is? Awesome. Now remember what I do is the final step, almost final. I copy the beginning and I copy the end. I don't copy the rest. I don't need to look at the intermediate steps. So I copy limit as x approaches 0 from the right from natural log y equals 4. Okay, what do I have to do next? Yes, I'm allowed to because it's a continuous function. That's a mandatory condition. So natural log of limit as x approaches 0 from the right of y equals 4. Now I have to think deep. Yes, 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 indeed. So we have the answer. Only natural log of e to the 4th will be 4. So that's our final, meaning limit as x approaches 0 from the right. What was it? 10 pages earlier, it was 4x plus 1 raised to cotangent x, and it happens to be e to the 4th. Okay, so let's summarize the steps. I remove, it's a function raised to a function, right? It's like we discussed, but I don't want to connect the concepts right now. But remember when we were trying to differentiate a function raised to a function, we had to denote the function blah, 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 and apply natural log. Same thing here, right? So we had a limit of a function raised to a function. We denoted the function by y. We applied natural log to both sides. We applied the limit to both sides. And when we were done, we copied the front and the last, and we figure out what the limit of the function was. Yes, please.
So
Steven?
that's saying that it's the limit of x as it approaches 0 from the right. It doesn't really matter that it's coming from the right in this case. If it was from the left, it would have essentially been the exact same process, right?
They're the same process, yes. But I can't say without looking carefully, I can't say whether the answer would be the exact same.
Yeah.
But it would, yes, the
Just like
procedure,
this.
if it's from the right or from the left or from either side, the steps are identical.
Okay.
Yes. Yes. Do you think we need another one, or is this clear?
Well, it seems like they all end with e being e to whatever
Because it's a
number.
function raised to a function,
Yes.
pretty much.
Okay. I'm good.
Okay, we move on. Okay. Now I can let you decide. We go back to 4.2 that we skipped last time, or we practice graphing functions in which we put everything together again. Everything, the first derivative, the second derivative, and all the information that the function, the derivative, and the second derivative will give us about the function. Would you like to practice that? Or we go back to look at 2 theorems. Very simple theorems. But no applications will be required on that.
Let's practice the graph.
Okay. So in that case, on page 317, and I cannot forget to talk about, yes, Caesar, go ahead.
Can I ask a quick question?
Any question?
So, is it always the case that it's e, the answer is going to be e raised to the coefficient x? Because in the first one it was e to -2, which was the coefficient of x in the first one. The constant of x in the first one.
Looking back, so your observation was that there was a coefficient here, and that's why we got e to the 4th. And on the previous one, it was -2, and that's why we got -2. I have to investigate a little bit further before I give you an answer to that. The reason you have something in there, and I would like to point you to. It's a very good question, and just give me 1 second because I want to show you where.
Should we try another one then?
No, yes, of course we can try as many as you want. I just want to show something. It's a very good observation, but I don't want to give an answer before I wanted to assign that problem or do it with you in class, and it's a very good question. That's why I want to go back now.
4.2.
Yeah, to 3 point something actually. Yes, I had that in mind. If I don't find it in the next 30 seconds, I'll stop because I don't want to waste your time. But yes, I wanted to discuss that with you. And it was when we discussed E. And here it is. Here it is. It's a very good question. Thank you so much for asking. So this is on page, page 223. Yes. So it depends. It depends. See, this is let me enlarge that. That's exactly what Caesar observed. It says, show that the limit as x approaches infinity, or I'm sorry, n approaches infinity from 1 plus, and that's, see, the coefficient is here, so this is 1 over n, and the number in front is that x, right, that you observed. So x is your coefficient. So the coefficient in our problem was 2 or negative 2 and then 4. So that's why the answer is e to negative 2 or e to the 4th. So that was one thing that I wanted to discuss with you in chapter 3. However, we couldn't really use it because we didn't know in chapter 3, we didn't know L'Hopital's rule. I used it and I showed you L'Hopital's rule, but we really didn't go into super details, right? So yes, I would say yes. Why I don't want to say yes 100% is because there are situations in which n approaches infinity, or in our case, x approaches infinity, doesn't matter, or approaches 0, right? So I want to analyze the two cases if it happens in both cases, when n approaches infinity and n approaches 0. But it's a very good observation. I had this in mind to show you. We can work on this right now if you want. So this could be one of the examples that we can work on. And we will see exactly your observation is very good. Perfect. Well done.